Hi, welcome to Recitation Week 12. Today's topic is still root locus, and I will be giving you three examples on how to plot the root locus of three different types of systems. The first example is given by this transfer function, and this is taken from Ogata book, example 6.1. Okay, so the closed loop transfer function, the open loop transfer function LTF is g of s times h of s, which is the same as g of s. So the number of poles, there are 3, number of 0, none, so n is 3. So there are 3 branches of the root locus. And the first step is to determine where the root locus will cross the real line. So we have this real axis, we have imaginary. The first step is to determine on which segment the root locus will be on this real axis. Okay, so let me label this quickly. All right, so the poles are 0, -1, -2, and the question is on which segment the root locus will be. To answer this question, we can do the angle test. So we can define some points a b c, and here is d. So we have 4 points. At point a, the angle is 180 degrees, 180, and all are poles. So we have minus 180, minus 180, which is minus 180 times 3. Okay, and this is an odd multiple of 180 degrees plus minus, so a will be crossed by the root locus. How about b? We have 0 here, minus 180, minus 180, we have this, which is doesn't satisfy the angle condition. C, we have minus 0, minus 0, and minus 180, which is again another odd multiple of plus minus 180 degrees, so we put check mark. And d, of course, here it is just 0, so 0, which is not. So we know that the root locus will cross point A and also point C. Okay, so we cross point A and point C. That's the first step. And what is the second step? The next step is to determine the angle of asymptotes and also the point of asymptote. Okay, so let's compute the angle of asymptote. So we can use the formula that I gave in the last lecture, and this is the formula, number of pole, right? So this is just np minus nz for k 0, 1, 2 up to np minus nz minus 1. So np is 3, nz is 0, so we have 3 minus 1 is 2, so we have 0, 1, 2. That means that there are 3 asymptotes. So let's do that for k equals 0. Then we have k equals 0, we have 180 degrees over 3 is 60. So plus minus 60 times 0. So we have plus minus 60. How about k equal to 1? 3. So plus minus 180 degrees, right? And the other is plus minus 2. 2 times 2, 4, plus 1, 5. So plus minus 60 degrees times 5, 300, or plus minus 60. Okay. Well, we have plus minus, so we just need to consider 1. And how about the point of asymptote, which is sigma sum of the real part of the poles minus sum of the real part of the 0 np nz, and then np minus nz. We know that we have the poles are 0, minus 1, minus 2, right? So 0 minus 1 minus 2 minus nothing over 3, so minus 3 over 3 is minus 1. Okay, yes. So from the last lecture, which is week 11, I didn't have this plus minus, so I don't have this plus minus, and so this becomes negative. All right, let me copy this. Okay, we have one point of asymptote starting at minus 1. So this minus 1 here will be the starting point of the asymptote, but we have 3 angle of asymptotes. One is 60 degrees, so say, let's assume that this is 60 degrees, and this is also 60. So this is plus 60, this is minus 60, and the other is 180. So just this yellow line represent, so these 3 yellow lines represent the 3 angle of asymptotes. This is step 1, this is step 2. So the step 3, we need to determine breakaway or break-in points. Alright, so we have k of s is minus 1 over g of s h of s. That means that k of s is minus 1 over 1 over this polynomial s plus 1, s plus 2, sorry, s plus 1, s plus 2, and you can simplify this into minus s cubed minus 3s squared minus 2s. What is the first derivative? dk of s over ds is minus 3s squared, right, minus 6s minus 2, and set them equal to 0, and we need to solve this polynomial, right? And we get s1 star, so you take the roots, 0.423, s2 star is minus 1.577, and we need to check which one of them k is positive on k of s. So k of s1 star, we substitute this into k of s. I get 0.3849, which is positive, and that's it. We do not need to substitute this. Why? Because if we look over here, the root locus has to cross this line segment between 0 and minus 1, and also the other line segment ranging from minus 2 up to minus infinity, right? And of these 2 points, we know that s1 star is right here between, it's minus 0.423, which is right here. So this point is of course on the root locus, but s2 star, which is minus 1.5, which is around here, the root locus doesn't cross this line segment, so this point we do not need to compute it because it's not on the root locus. And to check that whether this is a break-in or breakaway point, we need to compute the second derivative, and of course we can compute this. This is minus 6s minus 6, and then just substitute s with s1 star. We get minus 3.462, right, just negative. So that confirms that s1 star is a breakaway point. Okay, so we know that s1 star, let me copy this, copy, and I can remove this, and I can put point s1 star minus 0.423, which is around here, and then 1.423, which is s1 star, is the breakaway point. Okay, what is the next step? The next step is to determine the crossing of the root locus on the imaginary axis or j omega axis. we know that the asymptote is crossing the j omega axis at this point, but how about the root locus? So we need to solve it. The next step is one plus k g of s h of s, then substitute s with j omega, set them equal to 0. Okay, from here I get this polynomial. So j omega cube plus 3 j omega square plus 2 j omega plus k, set them equal to 0. Okay, you can simplify this. This becomes minus j omega cube. This is minus 3 omega square plus j2 omega plus k, and we can group them into real part and imaginary part. So the real part is k minus 3 omega square, and then the imaginary part is 2 omega minus omega cube. Since this needs to be 0, then this should be 0. This also should be 0, right? But assuming that if omega is not 0, then from here we can multiply this with 1 over omega. We have 2 minus omega square is 0. Hence omega is plus minus square root of 2. And how about k? K is simply, so omega square is 2, so 3 times 3 is 6, so k is 6. Alright, so the final drawing of the root locus is the following. I can, let me remove this. We know that S1 star is the breakaway. So around this we have something like that. Okay, now note that there are 3 branches for the root locus. The first one, the second one, and the third one. So we have finished with the plot of the root locus. Okay, now let's move on to the second problem. For this problem I have s minus 2, s minus 4, s squared plus 6s plus 25, and h of s is 1. So we know that np, there are 2 poles, nz, how many zeros? 2. So n, there are two branches, and the open loop transfer function g of s, h of s is the same. So we have what, s squared minus 6s plus 8, and then s squared plus 6s plus 25. Okay, this first step again is to determine where the root locus will cross the real axis. j omega sigma -1 -2 -3 1 2 3 j 2j -j -2j. Yeah, actually I need a bigger axis. Yeah, this is 4 -4. Okay, zeros we have 2 and 4. Yeah, 0 0, and the poles are complex actually, and the poles are -3 plus j4, so -3 and j4, which is somewhere here, and also -3 minus j4 here. Okay, so we have 2 poles, 2 zeros, and the first step is to determine on which segment on the real axis in which the root locus will cross. There are 3, and say we have this segment. For this segment we have 180 plus 180, so it doesn't satisfy the angle condition, and here we have 180, it satisfies the angle condition, and here it doesn't satisfy, so we have only the segment that satisfies the angle condition. It means that only on the segment the root locus will cross the real axis. Second step, angle of asymptote. But note that np is 2, nz is 2, so np minus nz is 2 minus 2 is 0. That means that there is no asymptote. So we don't have to compute the angle of asymptote and also the point of asymptote. So the next step is to determine the break-in or breakaway points. So we have k of s. So you can compute this. K of s is minus s square minus 6s minus 25 over s square minus 6s plus 8. So let's just compute the derivative. dk of s over ds is 12s squared plus 34s minus 198 over s squared minus 6s plus 8 squared. And the second derivative is 24 s cubed plus 102 s squared minus 1188 s plus 2104, and the denominator s squared minus 6s plus 8 cubed. Okay, all right, for this we need to set this equal to 0, and then we obtain 2s, s1 star, s2 star is minus 5.7186, s2 star is 2.88, 5 3. Okay, can see that S2 star, which is 2.88, is around here and it's on the root locus, whereas S1 star minus 5, it's not on the root locus. So we can just compute K of S2 star. So K is, it's 51.3118, just positive. And then we can substitute d square K of S over ds squared with S2 star, and that gives around 106.186 positive. So that means S2 star is a break-in point. So S2 star is 2.88, which is around here. And this point will be a break-in point. Okay. The next step, we will determine the crossing of the root locus on the j omega axis. So I will have this. So this equation is obtained from using this formula here. So 1 minus k times g of s times h of s, and then substitute s with j omega and set them equal to 0, and we will have this equation. And I can simplify this into minus 1 plus k omega squared plus 25 plus 8k, and that's the real part, and the imaginary part is 6 omega minus 6k omega. Okay, and again, if omega is not 0, then from here we know that k is 1, and since k is 1, then we can solve this polynomial here, which is omega squared is 33/2. That means that omega is plus minus square root of 33/2. Yes, that should be plus minus. Yeah, similar to this, we have plus minus square root of 2. Here we have plus minus. This is around 4.062. Okay, the last step, since we have complex roots here, then we need to determine the angle of departure or angle of arrival. But since we have complex poles, not complex zero, then you just need to compute the angle of departure. Why? Because remember that root locus, they start from the pole, right? So these two are poles, so the root locus will depart from these poles, and that's why we just need to compute the angle of departure. Remember that we have two poles, say P1 minus 3 plus J4, and P2 minus 3 minus J4. Hence the angle at P1, so angle of departure at P1 is 180 degrees minus the sum of the angle from the other pole and plus the sum of the angle with the other zeros, Ci. Okay, and I is not 1. And for this 180, the same formula, but we just need to set I is not 2. I. Okay, so let me copy this. Now let me remove this. So we know that this is 4, right? The height is 4, and from here to the j omega axis is 3, the length. The same with this. Now to compute the angle, so this should be the angle. I'm sorry. So yes, so we want to compute this, right? Phi P1 is 180 minus the angle of this point from the other pole, which is that pole, is what? Is 90 degrees, right? So minus 90 plus the angle from these two zeros. Okay, so we need to use trigonometry. So pull a straight line from that pole to the first zero, and similarly from that pole to the other zero, and let's label them. So this angle, let's label it as alpha. That angle, label it as beta. So this will be plus alpha, right? Plus beta. We just need to compute what is alpha and what is beta. Remember that from the j omega axis to 2 is 2, and similarly from j omega axis to 4 is 4, right? So alpha is the inverse tangent of 4 over 5. Why? Because 4 over 5, the length from minus 3 to 2 is 5, right? This is 3 times 2 plus 2. 3 plus 2 is 5, so inverse tangent 4 over 5 is 38. 66 degrees. Sorry, that's not alpha, because the angle of this poles to that zero is 100 degree minus alpha, so the other angle here, so that should be 180 degrees minus alpha plus 180 degrees minus beta. Okay, and this beta inverse tangent of, this time we have the same height, so we keep 4, but here we have 4 plus 3 is 7, which is 29.75 degrees. Okay, now we can compute phi p1. So we can 180 minus 90 plus 180 minus 38.66 plus 180 minus 29.75, and that is equal to 21.6 degrees. Okay, how about phi p2? Well, since we know that root locus is always symmetric with respect to this axis, the real axis, then this is simply minus 21.6 degrees. Okay, so that's it. So let me copy this again, and then we will construct the final root locus. Okay, so this is the break-in point. We know that the root locus will cross the j omega axis at, where is it, here, plus minus 4 points, so around 4. Okay, so 4 plus tiny bit here, and the angle is 21.6, so this is 0, so 21 is here, right? And let me draw it. Then it's something like that. So sorry, that should be blue, right? Sorry, green. So that should be green. So that's the sketch of the root locus, and don't forget the direction. So small arrow there, one goes there, one goes there, and say this is 0.8. Right, so that's the sketch of the root locus for problem number 2. Last one, 3. I have g of s minus 1, s minus 2, and then s plus 1, and h of s is again 1. Number of poles 2, number of zeros 2, so the number of branches 2. Yeah, so I remember that in problem number 2 there are 2 branches, which is, so this one, the first branch, and that one, the second branch. So that makes sense. And for this problem, the open loop transfer function is s squared minus 3s plus 2, and then s squared plus s. Again, we need to find the segment at which the root locus will cross the real axis. So this is, let's say this is j, this is minus j, and this is minus 1, this is 1, and this is 2, this is minus 2. Okay, so the poles, okay, we have 1 at 0 and 1 at minus 1, zeros here and here. All right. Okay, how many segments do we have? 1, 2, 3, 4, 5. Okay, we have 5. So let's do it quickly. How about this point? We have minus 180 minus 180 plus 180 plus 180, which is 0. Okay, so no root locus at this segment. Here we have 108 minus 180 plus 180 plus 180, so 180, which is an odd multiple of plus minus 180. So here, well, we have the root locus crossing the segment. Here no, here yes. Okay, that's the first step. Second step, asymptotes. Since we have the same number of poles and zeros, so there's no asymptote, so we don't have to compute the angle or the point of asymptotes. Next step, break in, breakaway. Okay, so k of s is minus 1 over g of s h of s, which is s squared minus s 3s plus 2. Okay, so let's compute the first derivative, dk of s over ds. You can use quotient rule. And it is equal to s squared minus 3s plus 2. And the second derivative, d squared k of s over ds squared, is minus 8s cubed plus 12 s squared plus 12s minus 20. Okay, the first step, so set this equal to 0, and then we have 2 points again, s1 star, s2 star, and s1 star is 1.366. This is minus 0.366. Okay, we know that minus 0.366 is here, so it is on the root locus. We need to compute s2 star, and 1.366 is here, so again, so both points are on the root locus, so we need to compute k of s1 star and k of s2 star. We can substitute s1 star here and s2 star here. We get 13.9282, 0.0718. Both of them are greater than 0. Then we need to compute d squared k s over ds squared. S equal to s1 star is, I got 128, which is greater than 0. And for the other point, s equals s2 star is minus 0.6632, which is negative. So that means that s1 star is break in is a break in point, and S2 star is a breakaway point. Cool. So we have one break in and one breakaway point. Okay, I can copy this. Paste it here, and let us indicate the break in. So S1 star is 1.3. That's 1.5. So around here, S1 star 1.366, and the breakaway is minus 0.366. Say around here is 2 stars. Cool. What's next? Crossings. Crossings on the j omega axis. Okay, so I have this polynomial. And we can simplify it into real part 2k minus k plus 1 omega squared plus j1 minus 3k omega equals 0. If omega is not 0, then 1 minus 3k must be 0, right? So that means k is 1/3. Substituting k 1/3 there, we get omega squared is actually 1/2. So omega is plus minus 1 over square root of 2, right? And that's actually plus minus 0.707. So let me copy this. Paste it here. Let me remove this. Okay, since we have real poles and real zeros, and there's no complex poles or complex zeros, then we don't have to compute the angle of departure or angle of arrival. The crossing is at plus minus 0.707, which is, this is j.5, maybe here and here. Okay, so let's draw the root locus. Okay, so that's the locus, and we have two branches. The first branch, say there, and the second branch there. Okay, so that's the final plot of the root locus for problem number 3. Okay, so we have solved the 3 problems. We have plot the root locus for these three problems. And that's the end of this lecture. If you have any question, please send me email. I'll be glad to help you, and I'll see you later. Thank you.